Hi everybody, today I'm going to talk about quantum exploration with Siesta, and these are the topics I want to treat today. Let's start with force-right electron density with Siesta. What's matter made of? Matter is constituted by molecules, and molecules are made of atoms. For example, here you have the salt crystal, which is made of sodium and chlorine atoms arranged over space, and then in a lower level we have the atoms, which are made of a nucleus, of protons and neutrons, and in the outer parts you have the electrons. The main question we want to address here is how can we construct molecules, crystals and bulk materials from these tiny objects. The rules of the game are given by the outer electrons, which tell us how to bond those tiny things together. The building blocks are the atoms, and for the force right we have 2 atoms of magnesium, 1 atom of silicium and 4 atoms of oxygen. Then, how do we have to repeat this cell over space in order to have a bulk material? We need 3 directions, 3 lengths, 3 angles, which constitute the so-called 3 lattice vectors. Why forsterite? Because it's an extremely relevant crystal in astrophysics. Here you can see the green color of it, and it is found in the inner regions of protoplanetary disks, which are made of dust and gas orbiting a young star, and this is the place where planets born. And forsterite enables us to reconstruct the history of these disks. Schrödinger equation. This is the main point of quantum mechanics. It's an equation which links the variation over time of the state of our quantum system to the dynamics of our system, which is contained in the Hamiltonian here. If there is no time dependency, no magnetic field, and for the low velocity regime, we obtain the simplified version of this equation, where in the left side we have the energy, the total energy, and here we have the kinetic energy and the potential energies. This equation is exactly solvable for hydrogen, so that's great news. But the bad news is it's not exactly solvable for systems bigger than hydrogen. So how can we do when we deal with big objects? Siesta, it's a way to solve this problem. We have to make some approximations. The atoms are almost fixed here, and we use the density functional theory, which states that the electrons are considered as diffused entities, and then the interacting electrons are considered as non-interacting electrons in an effective potential. So we pass from this situation where we have infinite potential wells to this situation where we have non-interacting electrons moving in these potential wells. It seems a bit artificial, but it works pretty well. Then the parallel computation obviously enhances the time and power required to perform these calculations. Finally, I would like to show you my simulations and my results. Here you have the isosurface for the force-right molecule. So we fixed a value for the electron density, and then we have this surface. Here you can see the molecule inside. And finally you can also see the system through a slice, and we can see the variations of the electron density over space. We reach the conclusions now. We have studied a crystal which is extremely relevant for astrophysics. Then we have solved a quantum problem using HPC. And then we will use also visualization tools to explore this quantum world. It's an innovative work since it links material science, HPC and astrophysics. Thank you very much for your attention. Bye bye.